Let's start. Okay, let's start. I'm very glad that we have Professor Steve Seitz from University of Washington. I think everybody knows of him, so I don't think I need any detailed introduction. But I'd like to say this. I'm the one who took him. He actually started at CMU, and I think I'm very proud that in a sense, I found him. Well, of course he was good.
Was.
But maybe, yeah. Was it good? Yeah. Maybe, let me tell you the episode. I forgot when that was, when you were about to graduate. And I was invited to give a talk at some conference or
France, I think.
France?
Yeah.
Yes, and he was also there, and he talked, I think after me or before me, I forgot. Anyway, as soon as I heard his talk, I thought that I should hire this guy. And I talked to him, and he said he has offer from somewhere. I said, hold on, don't take it. I will make a position at Carnegie Mellon, and I think I did. And he accepted, and he came here. So I think I'm glad that my eyes were of finding good people. Was good. So I'm bragging about this. So anyway, I think we're so glad that you come here, and you see we have a big audience.
Yeah,
Steve.
It's great. Thank you. Thank you. So I'm really glad I went to that conference. And of course, Takeo was my first boss, and so I still have to do everything that he says, I think, for the rest of my life. I think he's my... All right, so it's really special to be back here. Thank you so much for inviting me. This is a real treat. I just wanted to reflect a little bit back. So basically, as part of two groups when I was here, there at the time 2 groups, and now I think it's really nice how well they've merged, but there was kind of vision and graphics. And I was working closely with the vision group, and there's so many vision people that I couldn't even list them on the slide. So just here I'm just going to talk about the graphics group in particular. So here's the graphics group when I started in '98. And actually, this is not quite right. This is when I interviewed. This is the graphics group. And Andy Witkin, David Marr, Paul, sort of that helped recruit me and convinced me this was a great place. Then the week before I arrived, these 2 guys left. They went to Pixar, and Paul and I, where's Paul? There. We're the graphics group, and we were sitting up in Doherty Hall. And so this is what it was like, 1998, when I was a faculty member here. Now, hired all these incredible people, and it's really amazing to see, how this group has evolved and grown, really vibrant. And again, I'm just listing the graphics people and probably some vision people who do some graphics as well. And I'm also probably missing people from this list as well. But and then there's been people on the vision side, but it's really cool. And then now there's all these new buildings, and again, I'm missing some of the buildings too. So obviously I missed out. So these are some photos. I promised I would show you 1 trillion of them over the course of the talk, so I have to go quickly. So I've been doing I've been doing a bunch of talks over the years where I show these kind of hockey puck curves and show how many images are there on the internet, and there's billions and so forth on Flickr, blah blah blah. So last year I decided to do an experiment, just sort of back of the envelope calculation to figure out how many photos there actually are in the world. How many are there in total, all of people's photos together? And the basis is this kind of just amazing statistic from Facebook, which is that 250 million photos are uploaded to Facebook every day, which is just unbelievable. And this adds up to 7.5 billion photos each month. So how many of you have uploaded a photo to Facebook in the last month? Raise your hands. So maybe about a third of you. Okay. And I'm guessing of the ones who have uploaded photos, I'm guessing you upload a small fraction of the ones you actually take. I'm seeing people nod their heads. So just conservatively, if 12 photos are taken in the world, for every one which is uploaded, a dozen or so, for every photo that's uploaded to Facebook, then that adds up to 1 trillion photos taken every year. And again, this is, I think, very conservative. There's probably several trillion photos taken every year. So this is just a staggering number. So the next question is, so what do we do with 1 trillion photos? And the answer is they just go in this shoebox. Like, your grandparents have shoeboxes, at least mine did, in the attic with all these photos that they never looked at. And our shoeboxes are digital, right? So it's on our hard drives, iPhoto, Facebook. Our photos go in these places, and we rarely, if ever, look at them. Or a large percentage of them are never looked at. In fact, I have on the order of 15,000 photos of my 7-year-old son. And this probably sounds like a lot, but I'm actually not an avid photographer. I think most people who have a camera and kids take thousands of photos of their kids. And I don't, so half of those photos I've never seen. Because I just take the photos, and then at some point I transfer them to iPhoto, and then they're gone. Or the ones now my cell phone will upload to the cloud, and those photos go in the cloud. I never look at those photos. So a lot of my photos I've just never seen. So this is really pathetic, especially given how important we think our photos are, right? So if my hard drive died at home, and what's the data I would be most concerned about losing? It's my photos, right? It's not my email or my tax records or anything like that. So it's the photos which are the most important thing, even though I never look at these things. So it's clearly, there's something here. And I really believe that we're in the dark ages of photo management and browsing and organization. I mean, iPhoto is great for what it offers, but it's very, very primitive. And there's, I think, a decade from now, we're going to see dramatically better photo organizational tools. OK, so let me talk about, so this has really motivated my research over the last, the research of my group and collaborators over the last few years. And so I want to sort of start going through some of that. So let's look at some of these photos. And just, for example, Flickr, most of you probably know about Flickr, but it's photo sharing service on the internet. And people upload photos and tag them. And so if you type in a word like Rome, it will pull up all the images which have been tagged with the word Rome. And when I made this slide a couple of years ago, there were just over 1 million photos of the city of Rome, or that were tagged with the word Rome. And now there's like 3 million. But anyway, this is what these photos look like. So a typical photo from this collection looks like this. Okay, so this is clearly tourists who, in this case, a couple had a photo taken and then wanted to share it with their family and friends. Probably didn't intend me to use this in this talk, but the photo is public. It's on the internet. Anyone can use it. So the photo is probably not terribly interesting to people unless you happen to know these people, right? But it gets more interesting in aggregate, right? So if we have 50 photos of Rome, then we start to see there's the Trevi Fountain again. There's the Colosseum. There's the Pantheon. And here is St. Peter's, Vatican. So you're starting to see the sites of Rome. So it's like I'm summarizing Rome in a very primitive sense from this photo collection. However, 50 images isn't enough to cover Rome, so there's things missing. So for example, where's the Pope? It's this Rome. You should be able to find the Pope. So if you download 200 images, there's one of the Pope. And I'll spare you the effort of trying to find him. He's up here. So that's great. So we now have an image of the Pope, but we're still missing my favorite site in Rome, which is the Sistine Chapel. And so if you download 800 images, indeed there is one of the Sistine Chapel. And in fact, there are other images of the Sistine Chapel. And so now things are getting more interesting because we have multiple views and we can do more complicated analysis potentially of this. All right, but if you wanted to be more careful to make sure that you covered all of the sites, you might download 20,000 images, and the full collection looks like this. Of course, you can see absolutely nothing. Looks like random noise. And there, right now there are probably 3 pages which look like this just on Flickr. On Facebook, there might be 1,000 pages or whatever. So, all right. So the question is really, what can we do with this collection? So I'm guessing, given this audience, that most people here have heard of Sift. So who hasn't heard of Sift before? I don't want to intimidate anyone. I just want to, OK, so a few people. So let me just say a few words about it. OK, so this I consider to be basically the biggest breakthrough in computer vision in the last decade or so. And it's really an effective way of comparing images. Basically, it's a way of detecting features at different position scales. Every one of these little boxes is a feature. And the cool thing about these features is that this was developed by David Low and his collaborators, and it's sort of the culmination in years of work on feature detection and so forth, and descriptors. But the amazing thing about it is it allows you to very robustly match images. And in this case, we have images of the Trevi Fountain. The one on the left is taken during broad daylight. The one on the right is taken at night. And obviously, there are people sort of occluding the fountain on the left. In computer vision, these are kind of occluders instead of. And so, for example, but the key thing is you see these little squares, and these have been successfully matched automatically. So, for example, this little box here corresponds to this little box here, and this little box here corresponds to this little box. So even the conditions are totally different viewpoints, different illuminations, et cetera. These matches, you get good matches. And there's variants of this method that work in real time, 30 frames a second and so forth. So this is really amazing technology. I'm going to skip over the description of how it works because I think most people here know it, but I just want to show another example, which I love. This is a slide that Noah Snavely put together. So these are 2 images from the Mars rover, and you probably can't tell that these images overlap. But this algorithm can, and so the top left and bottom right are the features in common. And again, this can be run at 30 frames a second. So this is clearly a case where computers outperform humans in a visual task. So really amazing stuff. So anyway, so given armed with this kind of technology, we can basically take this unstructured collection of images and match the photos and figure out which images are in common. So with that, we can transform this collection into something like this. So here, every red dot is a photo from this collection. And just to simplify the visualization task, I'm only showing you 20,000 instead of the full million data set because it's too dense for the full million. And then there's a blue edge between photos that have features in common. Basically, photos that overlap are connected by a blue edge. And I'm using a simple clustering algorithm to lay things out so that images that are close to each other are spatially close to each other in this layout. And it's not using geometry or at all. It's just purely clustering techniques. So these clusters correspond to the most popular things in Rome. So one thing to notice is that we don't get one connected 3D model or not 3D model in this case, one connected cluster for Rome because people don't take photos of everything in Rome. They just take photos of the tourist sites, and they take a lot of photos of the tourist sites. So Trevi Fountain is probably overrepresented given its importance, but it's a very popular tourist site, so you have tons of images of it. And there's St. Peter's, the Colosseum, the outside of the Colosseum and the inside of the Colosseum. In this particular model, we're not connected. We didn't have enough features in common. But in other collections, we've been able to connect the Colosseum inside and outside. Anyway, so the structure of these collections is kind of interesting. So for example, why does Trevi Fountain have 2 clusters? So Trevi Fountain, for those of you who haven't been there, is just essentially just a facade. So there's not much to it. You wouldn't think it would segment like this. But these correspond to the daytime images. These correspond to the nighttime images. So you're getting some kind of photometric effects as well. And there's some kind of connections, some nighttime images that match daytime images enough that these two are connected. Yes?
Might there be also some kind of a bias in terms of the things that Sift matches particularly well, like planar facade with lots of structure, would get a bigger boost here than some very, kind of wiry and nasty object, things that might not get as much of a...
Yeah, so I think if you have things which are far from planar, then matching is harder, and you need more images to be able to transitively connect them all into a single cluster. Otherwise, they'd break up into smaller clusters. So I think, in that sense,
I'm saying that this is both how popular things are with photos and how matchable they are. Also,
yeah, I agree.
Sort of a factoring of those.
That's right. That's right. I think it's a good point. All right, so we have this, now we have images connected together, so that's interesting. We can start analyzing the structure of these image collections. But the next thing we want to do, we're interested in, is to see whether we can get 3D geometry from all these matched images. And so that's the next thing I want to cover here. And I'm just, again, I think since most people in the audience know about computer vision techniques. I'm just going to go over this very briefly, but this is another, I think, one of the biggest breakthroughs in the last decade or so from the vision community in photogrammetry. And there's a lot of work here, pioneering work here as well, on structure from motion. So this is a technique for recovering, given a set of matched features, like the output of the previous step I talked about. So I have some 3D scene which is unknown. I have features in this case 3 images, but it could be any number of images. And I want to determine from these matched features the 3D positions of these features, as well as the camera parameters, in this case represented by the orientation of the image plane and rotation, and the position of the optical center translation. And so my goal is to recover both the 3D of the points and the 3D of the camera just from correspondences. So this seems like a pretty hard problem. So the key to making this work is that if I told you what the answer was, okay, so if I told you here are the 3D positions of the features, and I told you here's where the camera was, then you could verify that my answer is correct by simply taking each 3D point and projecting it into the image using standard computer graphics, and you could measure whether the 3D feature projects to the 2D feature, right? In this case, the red point projects to a red point in each image. In practice, there's going to be some amount of error between the projection and the measured feature, and that's the error that I'm going to try to minimize. Okay, so that basically boils down to I can write a function f, which is called reprojection error. All the distances between the measured and the projected features over all the images and over all the features. And I want to minimize that with respect to the camera parameters in the 3D scene. And I'm not going to go into details, but this is what these classical computer vision books now cover how to do this at large scale. Okay, so this stuff is really this stuff really works. We had to do a bit of extra work to make it work for photo collections, for unstructured photo collections. Most of the original work was done for videos. And to get it to converge is not easy, because even though you can write an energy function, it ends up being this large nonlinear least squares problem. And so like any nonlinear problem, you have to initialize it well. And there's sort of a black art into figuring out how to initialize these algorithms correctly, I think, as many of you know. But the recipe that seems to work pretty well is you find sort of a really good initial pair to start with. You optimize those, and then you gradually add more images at a time. And here's a time-lapse view of what this process looks like for the Trevi fountain. We're showing more and more images appearing, and then the model kind of converges. And I'll repeat this video once or twice. Unfortunately, it doesn't run this fast. But in newer versions of this software that we've developed, it kind of starts to approach this speed. We're getting it to run incrementally as more images are added. And so now we have basically, there's a toolkit called Bundler that Noah Snavely wrote, and now it's distributed on our website. So if you have your own set of photos, you can run this on your own set of photos, and it'll create 3D models automatically. Lots of people are using this. So Noah, the graduate student who developed this with me at the time, co-advised by Rick Szeliski, is now a professor at Cornell. All right. So right after we did this work, we also did sort of a graphics version where we created some cool renderings, and I'm not going to have time to show you them, but basically a way to browse photos in 3D, which makes it photorealistic. And we licensed this to Microsoft as the basis for something called Photosynth. And so now you can try this out yourself. If you take a lot of photos of an object or a person or whatever, you can upload them. You can actually download this Photosynth software, and it will sort of create a 3D visualization, and anyone can view it on this website. So it's pretty cool. Try it out if this sounds interesting to you. All right. So that's a few years ago. Now, in parallel to the effort at Microsoft, we kept pushing on the research side of this. And one of the things we wanted to do was coming back to this question of, can we do the city scale? So can we take all the images in Rome and create a 3D model of the whole city just from people's vacation photographs? And in some sense, the answer is yes. I mean, the algorithms don't really care about what you're reconstructing, whether it's an object or a city, but actually making it run at that scale required a lot of engineering work and a bit of research. And so we spent basically a couple of years trying to get to the point where we could do this. And as we got closer and closer, we decided to up the ante to see if we could reconstruct the city in a day, just so we could say we built Rome in a day. And the idea was to use originally 1 million images and 1,000 compute cores. And this is around 2007 or 8. And at the time, finding 1,000 compute cores wasn't easy. Our collaborators at Microsoft had just built this new compute cluster that was completely untested. And so they allowed us to be the first users of this compute cluster. So this is positives and negatives. The positive side was we had this 1,000 node cluster to ourselves for for essentially a couple months. Negative side was we were the testers, and so 1,000 things broke, and we barely got this paper out in time. Literally the day before, we didn't know whether it was going to work. But anyway, this could not have been possible without Microsoft's support. So Samir Agarwal was the lead on this project, and we was able to build a system that does reconstruct an entire city in a day. And without going into details, I want to show you just some of the results. And again, unfortunately, we didn't get a complete model of the whole city of Rome because people don't take photos of every little nook and cranny. We get photos of the largest tourist sites. So the biggest cluster, the thing that more people take photos of than anything else in Rome, is the Colosseum, maybe not surprisingly. And this is what that reconstruction looks like. So every one of these little boxes down here is a camera frustum. So this is the camera position, and this is the orientation of the image plane. And so if you took a photo of the Colosseum, you upload your photo to Flickr, a few years ago, you're standing somewhere in this collection. So we figured out where you were standing when you took your photo. And don't ask me which one's you. All right, so this is the largest cluster. I don't think it's as interesting as the next one. So this is another chunk of Rome. Yes?
Did the pictures have to be tagged Rome, or did you detect the thing?
No, they had to be tagged Rome. They didn't have to be tagged Colosseum. So we only used photos which are being tagged Rome. But now, I mean, with geotags, you can just look for geotagged imagery of the place.
Did you use all the images, or there are a percentage of images that are hard to match and you just...
We just took all the images. Although we didn't end up getting to 1 million scale. In this case, we only had 150,000 on that collection. There's a follow-up project that actually did 3 million from UNC. All right, so this is a cool, I think this is my favorite model from this collection. This is St. Peter's, and what's neat about it is it's actually the inside of St. Peter's, but this is a rendering from overhead. So it's like this impossible rendering of the inside of an object from the outside, like a Hitchcock-like view. But you'll see as we zoom down to ground level, here we are inside the cathedral, and you see where people are standing, and you can look up in the dome. One of the things you'll notice is that there are all these cameras scattered up here. And if you've been to St. Peter's, you may remember that there's basically a staircase that goes up to the top of the dome from the outside, and you can look in the dome from the outside through these windows, and that's what those cameras correspond to. So there's people standing outside looking through the windows. So the algorithm does make mistakes, but in this case, these floating cameras were actually correct. Or we believe they are. All right, so, okay, so I sort of, I joked that we did this project so we said we could say we built Rome in a day, but the real advantage to doing this is that the next day we can reconstruct another city. So the next day we did Venice. In this case we had 250,000 images, a little bit more. And this is the largest chunk of Venice. In fact, this is the largest model that we can reconstructed, period, which I think is the largest model of its type at the time from unstructured imagery. So this is 14,000 images from Venice. And there's zillion people all over the place, incredibly dense. If you've been to Venice, this is like pigeons on the ground,
Pigeons with cameras.
Pigeons with cameras, excellent. That's a good idea, actually. Anyway, so this gives you a sense of the scale of these kinds of approaches. Now, I was hoping to get a more complete model of Venice because you can actually, you go through the canals, and actually this is connected through a canal. But the matching wasn't good enough at the time that we had to, I believe we could still probably get a connected, if we scaled it up a little bit more, I think we could connect a lot of Venice. But here's another chunk. Here's the Grand Canal. We're sort of flying down to water taxi level, moving up to the Rialto Bridge. And this is cool. I mean, the neat thing about the Rialto Bridge is that people take photos from every single possible place along the bridge. One of the things which is interesting about this that we haven't really looked at carefully is, this tells you a lot about the distribution of photos that people take in the real world. And it'd be interesting to sort of mine that and see what you could find out from, GPS also gives you that, but this has much higher granularity, much more accurate. It gives you orientation as well. All right, more recently, we started looking at, can we increase the resolution of these models, the details? And these are the kinds of models that we've been reconstructing so far, and these are pretty sparse. Now there's other technology that I think most of you are familiar with, stereo, which can give you much more detailed models. In particular, there's in parallel with all this progress on structure from motion methods and Sift and so forth, there's been a huge amount of progress in multiview stereo over the last, I would say, 7 or 8 years. To the point that now you can reconstruct models that have the accuracy of a laser scan just from unstructured. So just from people's vacation photos, I can essentially laser scan the Colosseum, and the accuracies are within 0.25% to a laser scan. So this is really amazing, and there's work in my group and other groups that enabled this. Yasu Furukawa is the one I'm highlighting here. He's a postdoc with me at UW. Anyways, we're able to get these much more detailed models. And to give you a sense of comparison of before and after, this is one comparison, but I think a video does a better job. So here's St. Peter's, the point cloud before, and here's the dense reconstruction from stereo. And it captures a lot more detail. And of course, we can color the points as well. And there are holes in places and so forth, but I think it's pretty impressive what these stereo algorithms can do. So again, this is just reconstruction of St. Peter's from people's vacation photos on the web. Here's another example. This is the Seine San Marco Plaza in Venice example I showed you before. The same data set, but reconstructed with stereo instead of structure for motion. And again, it's very, very detailed. So you can really make out the minute structures of these sculptures, statues. It's a clock tower. You know, and there's places which are less photographed, so people take fewer photos of the back of the plaza, and so this part isn't modeled quite as well. And there's, you know, cruft and tables and chairs and stuff that that should, you know, so there's certainly opportunities to improve these models significantly beyond what we've done. But this gives you a sense of kind of the current state of the art in 3D reconstruction from unstructured photographs. I guess there's one more segment here where we pull out, I think. And you can see all the photos are from the ground, so the tops of, you know, buildings are all missing. So I'll get back to that point later on.
Is this, I should say, the coloring, is it view-based, display-wise?
Yeah.
Is it, you know, textured 3D object is displayed, or for each view you are actually changing the display?
It's a textured 3D object. So every point in the model is assigned the average color of the pixels that it projects to.
So it has a single color? A
single color, yeah. So it's kind of this impossible shading, cartoon-like shading, because we're essentially removing all, you know, illumination of dependent effects. And I'll come back to that as well. All right, so okay, so I had the opportunity a few years ago, I guess in 2010, to start a group at Google to do essentially 3D modeling and similar technology. So they were excited about, you know, what we've been doing in the work I just described, and they said, well, why don't you come to Google and start a group to do something similar? And they said, you know, you can stay in Seattle. There's an office in Seattle. You can hire whoever you want, and you know, it was like too good to be true. So you can, you know, work on Google Maps, which is one of my favorite projects, you know, products, and so this is a really enticing proposition, and I was excited to make something happen there. So let me talk a little bit about what it's like to do that. So just to give you a sense of the task, so we decided that what we wanted to do was sort of figure out when you do a search for, say, Trevi Fountain on Google Maps, it should present you with something exciting and visual, because it's a very visual place instead of just giving the address. And so what should that be? What's the ultimate, you know, visualization of Trevi Fountain that sort of makes you feel like you're there? You know, so that was kind of like our original goal and, you know, dream of doing something at Google. Now, there's a number of reasons why this was dramatically more difficult than we originally anticipated. The first one, which nobody happened to tell me about, was that actually Google Maps doesn't support 3D. It's based purely on pre-rendered image tiles, which are served from the server to the client, right? And so everything is basically pre-rendered and static, and you just load it up. And so the first thing we had to do, like us and a bunch of other teams at Google, was throw out all of the 3D Maps infrastructure, the client infrastructure, and replace it with something that supports 3D. So we and a bunch of other teams spent basically the first year just doing that. And the result was something called Maps.gl, which I'll demonstrate shortly, which is implementation of Google Maps, which is very similar to the previous implementation with a couple bells and whistles. But the main difference is that it supports 3D rendering. So everything is done in vector graphics instead of you know, pixelated stuff. So anyway, but so there's a lot of challenges with this problem. So just showing the user the ultimate immersive visualization turns out not to be what you want on Google Maps. So let me kind of break this down a little bit and tell you some of the requirements for maps. So the first thing is that it's really important that we give spatial context. So people come to maps because they want to know where something is with respect to where you are. So we need to preserve that. And so if we're going to show imagery, it really has to be in context of the map and other imagery and so forth. The second thing, which I think is maybe more subtle, is that it has to be fast, right? So I think most maps users don't go there to explore. I mean, you might do it occasionally, but most use cases, you want to know, where is this thing, and you want the answer in seconds, So it has to be fast, okay? So we can't just do some, let's fly around, Trevi Fountain for 15 minutes. It has to be in seconds, over in seconds. It has to be incredibly simple to navigate, and this is another big challenge, right? So even Street View I wouldn't say is terribly easy to navigate. It's relatively easy, but not, lots of people have trouble with it. So, and obviously the UI could be improved and so forth, but this is something that, like a kid should be able to navigate, a grandmother should be able to navigate. So how do we do that? And finally, we want it to be immersive and cool and exciting, and it has to scale to thousands, tens of thousands, millions of places eventually. So these are some very difficult demands. So we came up with, just to make a long story short, the following project, which is to essentially create a movie. So we want to create a 3D movie of Trevi Fountain. So why a 3D movie? Well, we can give spatial context by kind of connecting it to the map, kind of swooping into the scene and showing you the relationships in 3D between different images. We can make it as fast as we want because we're creating it. So if you want a 10-second movie, we'll give you a 10-second movie. Movies are very easy to navigate. You just say play or stop. I'll show you some examples of immersion, and we can make this run on tens of thousands of sites. So let me give you a demo. Hopefully a wireless connection still works. OK, so here's Google Maps. And if you want to try this, you have to be running Maps GL. And it should say Maps GL enabled in the bottom left-hand corner. If you haven't tried it, in the bottom left-hand corner if your browser supports it, it runs on most browsers right now, and you have to have a decent graphics card. It'll allow you to opt in. Anyway, so let's go to Trevi Fountain. That's interesting. OK, so you see in the left-hand panel this thing that says take a photo tour. And so let's just go ahead and do that. It should fly me into Trevi Fountain. And so here's a tour which is of the fountain. And it's going from one photo to the next. But you should be able to see some 3D transitions here. It should look 3D as the object is rotating in front of you. And so you're seeing images at nighttime, images at daytime. And I think it's giving you a reasonable sense of the size of this fountain. And you'll see tourists in background to see the scale. And so we're basically finding the key views of this thing and then presenting them to you as a movie. So again, it's a pretty short and I think compelling summary of Trevi Fountain. So we have quite a few of these things. Like there's a bunch of controls. You can play nearby tours. You can rate tours. So please do rate them. This is one of the good ones. There's others that are not so good. So we can try to improve. If I click on nearby tours, it will give me this. I don't know why this thing won't go away. It'll give me this. Here are all the nearby tours on the map. And here's a list of them. And I can zoom out and see more. So here are all the tours in Rome, and there's a couple hundred some odd tours. I think it's compressing. If you zoom in any region, it'll show you more. And we can zoom out even further. So here are the tours in Italy, the tours in Europe. What's it doing? And so forth. You can keep zooming out see all the tours. So we have quite a few of these things. Another way to get to these is if you go to maps.google.com/phototours. Oh man, are you serious? Wow, that's the first time I've seen that. Okay, well maybe we can see. Demos never work the way you want them, isn't that the case? So let's see if this works. Well, why don't I show you another one? Fremont Troll. So here's another tour, sort of a so-called Easter egg tour, where this is in Seattle. This is one of the landmarks in Seattle, the Fremont Troll. In this particular one, we took the photos ourselves. It's the only tour of the type where we took the photos. And you'll see the team that worked on this. This is us. Injected. This is the group. This is Samir Agrawal, the guy who did Rome in a Day. There's Yasu Furukawa, who did the 3D stereo work, and several other members of the group, and then we magically disappear. Anyway, so a lot of examples, and I'm really disappointed that this doesn't work. But at least I got to show you a few tours. Anyway.
Do you have an example where it doesn't work that well?
Oh, it always works. Are you kidding? So, well, let's take a look. So going back into this one, let's go look at the statue of Lenin. I think if you just say next tour enough times, you'll see examples. So here's heads cut off, but it's still a decent tour, I think. Let's look at the next one. Gasworks Parks. I think this one's less successful.
Engineering question.
Yeah.
So why 3D?
Why do you need 3D at all?
Yeah.
Well,
just playing me a movie.
Yeah, but the source material are raw photos. Are you talking about using YouTube instead?
I mean, if it's just completely canned, I'm wondering what the motivation for 3D.
Well, the key thing, the main thing that it gives you the Bruce Lee's gravesite. This is cool. I haven't seen this before. It's in Seattle. It gives you, I think, some spatial context that's missing if you just show one photo after another. So we wanted to show you how the object, so for example, we can show an image of Trevi Fountain, an image of the people looking at Trevi Fountain, but unless you see where the people are with respect to the fountain, it's hard to sort of visualize the site. And we want to be able to do that. Yes?
Especially on that issue, why can't you imagine with all these images running around, you have some clever interpolation among the images from different locations to give that sort of tour guide view? But
this is an interpolation, right? I mean, we're using the geometry to warp from one photo to the next to just give a little bit more context.
So 3D helps your interpolations.
Yeah, exactly.
I think the question is, why not? What's wrong with using a homography instead of a polar?
Yeah, it looks much worse. Well, to be honest, I mean, there are cases where the geometry is erroneous, and I'm trying to find one where you really, if you use homographies, you end up getting these ghosting effects, which you've seen before. And when the geometry is good, the geometry makes it look dramatically better. You really notice the difference. In cases like this, essentially, we are using homographies. It sort of falls back on when there's no good geometry. In this case, the images are taken from nearly the same viewpoint. It's essentially using planar proxies. All right. OK, so let me get back to this. All right, so this is a cool example of a research project that started at the university that we were able to kind of transfer to Google. And this was done by a graduate student, Avnish Kushal, and undergraduate Ben Self, working with a bunch of us at UW and Google, and published at a conference this year. And lack of time, I'm not going to have time to go into details here, but it's essentially what we do is we sort of cluster the photos, find canonical views, kind of the most popular views of the scene, and then we solve a version of the traveling salesman problem to find paths, sort of optimal paths through these views to create literally a tour out of the photo collection. So I'm going to skip this. And this is created automatically from public Picasa and Panorama photos. So if you take photos, you upload them to Picasa and you make them public, then and they're good, then there's a chance that they'll appear in our photo tours. I wanted to make a plug to this this piece of code. So a lot of the optimization work that we had to do to make this work was developed by people in our group, in particular Samir Agarwal. And he's open sourced the code. So this is not just structure for motion, this is a general nonlinear least squares solver. And it's really, really good. So it solves general nonlinear least squares problems. It handles sparsity. There's implementations that work on cell phones as well as PCs. It's multi-threaded. It's totally open source. It does automatic differentiation, robust loss functions, all the bells and whistles. So if you have a problem and you want to sort of graduate beyond MATLAB, this is the tool for it's really great. It's starting to get a lot of use. So I was really excited to be able to sort of give back to the research community with this. All right, so so I think people often ask me, they'll sort of say, okay, so now we've solved 3D reconstruction, we can move on to object recognition or some other crazy problem. But it turns out there's way more to do here. That even though we've seen all this progress in the Apple Maps, that got all this publicity, and all these other companies have variants of that. And these models look really good, but I think people have really picked apart Apple, I think, unfairly because of artifacts in these maps. So here I'm actually showing you some Google results and this one's from Google Earth, sort of a bad reconstruction of a building. Here's one from Apple of this shiny, impossible from computer vision standpoint to reconstruct this, right? And you get this horrible blob. Bridges, roads tend to be very problematic because there's motion, and so you get bad stereo artifacts where the ground is actually, you can't see it well in this projector, but it's attached to the bridge. It's like an earthquake occurred. Repetitive structures like roads are very, very difficult. So there's countless, and I think this is unfair because I think these maps are beautiful, and it's really success of stereo vision. It's impressive how good this technology is from C3, a company that Apple acquired. But it really points out that we're not there yet, and it also the truth is that there's this phenomenon that the closer you are to photorealism, the more attuned you are to limitations. This is known popularly in robotics. The uncanny valley effect, originally applied to people, that says that things which are not very realistic, like stuffed animals, the more realistic you get, the better it is, up to a point where if they get really close to human-like but are not quite human, like a zombie, then it's very disturbing. And there's a similar effect that occurs in 3D reconstruction. So getting this last 10% is by far the hardest problem. I'm not going to have a lot of time on this, but there's a lot of major open research problems in this space. I'm going to show you some very preliminary work that we're basically in progress on trying to address some of this. So here's a photo of Colosseum in our latest reconstruction. And so now we have the area around it because we're using aerial imagery, we're using street view imagery, we're using ground-based imagery to try to get as complete a model of the Colosseum as possible. And we're also modeling the illumination. So now we can match this reference photo by changing the illumination of the model to match. This is, by the way, work at the University of Washington, not at Google. And here we're going to fly into another. You see, like, you can actually read signs. These are very detailed models. And there's still artifacts, but I think its projector's fairly dark. And here's the reference photo. So I think we're not quite there to photorealism. I mean, it's still, you can detect the difference between a rendering and reality, but we're getting a little bit closer. And we decided to, try this Turing test. Well, the Turing test is, if I give you two photos, a rendering and a photo, can you tell which is real and which isn't? And so we gave a bunch of pairs to mechanical Turk workers to try to evaluate whether they could tell which one is the photograph. And in this case, it's actually, you can imagine people making mistakes. We're actually kind of close. So we had 20 different subjects rate each image pair. And these are some cases where we did pretty well. So in case you can't tell, the top row are the photographs, the bottom row are the renderings. And about a third of the people were fooled, which I think is pretty good for these cases. And the majority of people were fooled for these cases. And you can sort of see why in some cases. Like in this case, our rendering had blue sky, and the other one didn't. So they actually thought, well, it's Italy, it's probably blue sky. So that was a bias. And similarly, this, the sky up here looks kind of fake, even though it's, well, who knows what happened, what they did Photoshop to the photo, but it doesn't, almost looks too synthesized, whereas the reconstruction, more people thought it was realistic.
So you're not actually putting in a sky model?
We have a very primitive sky model, yeah. So here are some cases where we did poorly. Basically, you didn't fool anyone. And here, it's obvious why, right? I mean, if there's people, we never have people in our reconstruction. So, but this sort of suggests, some of our conversations earlier today about, if we simply put in people, in different random places in the renderings, maybe we would get better scores. But there's other reasons, like we're missing, missing the water, and God knows what's happening. So there's all sorts of random geometry here. So obviously there's a lot more work to go here. So this is still, I think, a grand challenge. Let's see. Maybe I'll say a minute on semantics. I mean, right now we're just reconstructing kind of like a soup of polygons. It's just a bunch of geometry with no information at all about the scene. But for example, if you have this, here's the Pantheon, all of the stuff, or a lot of it has names. This is a painting by someone, here's a statue by someone else. These are, the tomb of Raphael is in here somewhere. So you'd like to be able to label all this stuff. So, well, if you look at Wikipedia page on the Pantheon, there's tons of information about the Pantheon. And in particular, towards the bottom, it actually gives you kind of a very detailed, exhaustive list of everything in the Pantheon. So let's see. So for example, the first chapel on the right, the Chapel of the Annunciation, has a fresco of the Annunciation, blah, blah, blah. On the left side is a canvas by so-and-so. On the right wall is this piece of art. The second niche has, so it basically kind of goes through the entire contents of the Pantheon and tells you what everything is. So wouldn't it be great if we could, if we could have a computer read this and somehow correlate this with the geometry? So we have all this text data, we have all this image data and 3D models. And there's also, in addition to this, the sort of key additional piece is there's lots of data of images correlated with text. So lots of web pages which have titles of, lots of web pages that have a photo with a caption saying what that thing is. And that's basically what image search tells you, right? So if I do a Google image search on the Annunciation, it will give me photos of the Annunciation. So the basic idea is you have a computer, sort of a natural language parsing technique to just compute a bunch of candidate objects from this list, do Google image searches on all of that stuff, and connect the images that are retrieved, use feature matching with the geometry. And that gives us pretty good results. So I'll show you some of the labelings that we get. Here's the labeling of the Pantheon. We're able to figure out that this is the Assumption. And these are a bunch of different objects that we've, the tomb of Umberto, et cetera. So these are automatically computed from the Wikipedia pages. For Trevi Fountain, we're able to label a bunch of stuff on Trevi Fountain. Sistine Chapel is a crazy view of the Sistine Chapel. And here are all the objects we're able to label. And Library of Congress. This is a sculpture area in Florence. And this one shows some of the limitations. Here we're only able to label 3 of those sculptures. In fact, there are a lot more. So this is sort of the ground truth, and you can see that we're still far from being able to get good enough retrieval on this. And we're also getting false positives, which I haven't been showing you. Here are a bunch of things that we labeled which are not actually objects. And so this is another area where we need improvement. So this is work by Brian Russell and Dan Butler. Brian is a researcher at UW working for Intel, and Dan is a graduate student. And anyway, so there's a lot more to do here. We made a lot of progress. I also wanted to make one last comment, which is just as I admire how the group is growing here, I'm super excited that, I was the last person who we hired at the University of Washington in either vision or graphics, and that was 14 years ago or 12 years ago. This year we hired 4 people in vision and graphics. So Ollie, who is a postdoc here, and these folks. And so if you're an undergraduate interested in graduate school, or you're an advisor who knows good undergrads, please send them to us. All right. Thank you very much.
Questions?
You have shown that all the structure from motion and photo shooting stuff. I mean, you show like image as a spatial sampling of the space. I'm wondering, actually, image is not spatial sampling. It's like spatial temporal sampling of the space. I'm wondering that if you have used any timestamp of the images or timestamp for uploading time. I mean, would it be good information to improve some other tools?
Can you use timestamps? So we haven't thought of a way to use timestamps effectively, but I think if you had a version of Street View, it'd be great, for example, to have a street view of New York during the winter as well as during the summer, so you could see, depending on when you're visiting. And certainly timestamps, date stamps could help there. And similarly, you could use that kind of information. So for dynamic events, I think it would be interesting if you had a concert or something like that you wanted to summarize. You could use that. But beyond that, we haven't really thought about it. Yes?
Instead of using pictures from Picasa or Flickr, have you tried to use the street views? Because I think street views can provide you more advanced.
Yeah. So yeah, good point. So I think for the Rome data set, if we could use Street View, then that would allow us to connect a lot of stuff. And that's definitely something we're really interested in. Just haven't had a chance to do it yet. Paul?
You're relying on tagged images, correct?
Yeah.
So you'd have a much larger pool of images if you included untagged also.
Yeah. But it's also a larger pool of images, like a trillion images or whatever it is, right? So tagged was a low-hanging fruit. There are a couple of other hands. I don't know who is next. Kivon or?
Well, I'm just curious if these are static worlds.
Yeah.
And video, entertainment, and everything it's the liveliness of the world that
right.
make it very interesting. So I'm wondering, it seems like a logical place to go would be if you're walking down, Broadway in Manhattan. Not only is it a beautiful rendered view of the static stuff, but we're synthesizing a crowd around you.
Yeah.
Synthesizing audio, and it just
I totally agree.
like
yeah. So it'd be great to have some kind of moving experience. Even you guys joking Trevi Fountain. So the Noah Snavely, the guy who did all his phototourism work, he had never been to Trevi Fountain until this year, and I went with him to Rome to visit, and he saw it for the first time, and he just wow, this looks nothing like my visualizations, And so part of it is the scale. I think that's a big thing. The other part is the fact that there's water, moving. There's tourists. There's people eating gelato. It's very dynamic, right? So I think that I think that there's the video data tends, historically hasn't been as high quality, and so that has been the trade-off. But now that there's HD and so forth, it would be really interesting to geolocate and reference that data as well and show it somehow.
So can you talk about beyond Sift? So I noticed that the work with Brian with labeling.
Yeah.
The place where it fails is you have these beautiful white statues with not much texture on them, and that seems exactly where it's failing. So do you see something happening in the matching story to deal with these low texture, non-planar things?
Yeah, I agree. I think I don't have a good answer to that. I was hoping you could solve that problem. But absolutely, I mean, there's places where statues are particularly problematic. I mean, for this labeling task, you don't need too many features to get it right. And of course, if you have really high resolution images, you have texture everywhere. So there's some hope that we can get a reasonable way but it's not going to be as robust as if we could actually handle this untextured stuff. I think you were first in the back there. Yeah.
Do you guys have any plans to use non-visual databases like height-map data or like river maps or something like that?
Yeah, so there's a lot of 3D models already out there, but they tend not to be either high. They tend not to either be the height. The GSMs and height maps of terrain are very low resolution. So for the most part, everyone's starting from scratch. Yeah, but some of the hand-modeled stuff, like there are a lot of hand-modeled buildings, and so in Apple Maps and Google Maps, what you're seeing is actually a mix of stereo and then hand-modeled stuff in places where it breaks down. So those do play a role. Yes, I think you're next.
You started your talk of complaining about digital shoeboxes, right?
Yeah.
It seems like that's still a problem right now. It's not the trends aren't changing. Do you have any ideas of how to change that? What are the things that Google could do or Microsoft could do that could change how much people share?
Yeah, in fact, so I have another version of this talk where I talk about modeling personal photo collections. This work that Ira Kamelmacher did with me. She gave a talk here earlier this year on sort of face movies and face modeling, and that was more kind of digging into your personal photo collections and creating new ways of presenting your own photos to you in interesting ways. So I mean, I think there's a lot more to do in that space, and I don't claim to have the answers, but I would really like to have effective search, for example, for my personal photo collection, the way I can search the internet for any image on the internet, but I can't do that in my personal photo collection. Takeo, I think you had a question.
Yeah, you mentioned some of the problems of like glass or mirror-like objects.
Yeah.
Some of them may be removable simply geometrically by not consistent among many, many views, or eventually you may need to, part of your lower level semantics, like this is actually glass or mirror object. You didn't talk that as a challenge?
Yeah, so it was, I very briefly glossed over it. Basically there's a zillion corner cases, glass, water, all that kind of stuff. So all the complex cases here, and this is stuff that vision researchers have sort of swept under the rug. I mean, there's a smattering of papers on it, but you basically, to make it work at scale, you have to handle all this stuff. I mean, the problem is coming up with algorithms that are good enough that it works, the vast majority of the time. And so I just don't think that we have that yet in computer vision for glass. But certainly you could, I think you could do like window detection. It wouldn't work for this crazy mirrored, beam thing in San Francisco, but yes.
Have you ever had events where there's a lot of photos taken out of place at one time, but then not taken
Yeah. So in fact, there was a really cool photosynth of I think Obama's inauguration speech that was, these are photos of taken at different times during the speech where you can kind of zoom around through the scene. So there's some examples of that.
Has it ever happened in a place that you wouldn't get Photosynth, so it's biasing at only one point in time.
So that is what?
So it's a biasing. It only gives you one point in time almost here.
Because there's too much motion or something like that?
You think you answered.
Okay. Yes?
Have you considered, since you have a trillion image, then you are basically, as the number of image grows, you are having more and more near duplicate image.
Yeah.
And also a large, and also are you making use of a large amount of untagged data? Can you learn tags and can you make use from them?
So yeah, to be honest, we're not really using a trillion images yet, but I was just saying there are a trillion images. But yeah, so most of them, you know, there's like, I don't know how many hundreds of thousands of images of the Trevi Fountain, and almost all of them are the same, you know. So yeah, so the more, you know, advanced implementations of this stuff will do duplicate detection and try to minimize the processing to scale up. Then your second question is, can you handle untagged imagery? Yeah, so I think untagged imagery is really hard. You just have to be able to have matching techniques that are effective at sort of world scale. If you don't have any, if you have GPS data, then there's hope, you know. But if you have no GPS data, you have to be able to take 2 random photos in the world and see. So it's this kind of, you know, with a trillion squared is a complexity, right? So, you know, it's a hard problem. Yes?
So for the semantic part of Brian Russell in the last part, you were getting a lot of the data from just reading the web, basically. Have you considered that there might be organizations that might have a vested interest in perhaps having lots of these things tagged? Have you looked? They might be able to provide better, more high quality data.
Yeah. Yeah, so absolutely right. So I think like some expert on the Pantheon could go through and manually tag these models. And since you just have to tag it once, then you're done. So I think, yeah, that's a good point. I think this is just sort of an academic, we're interested to see how much we can learn from the text. But we're also very interested in enabling sort of manual tagging to both correct and improve these models. But definitely, yeah, that's something we also want to create these like manual. So the Brian Russell, the one who did this, you know, he's famous for having done this label me thing, which is where people manually tag things. So this would bootstrap such an effort. I don't know who's next.
Let's do a couple more.
Okay. Yeah, sure.
So currently on Wikipedia, there's latitude and longitude coordinates associated with places and objects. Do you think there's an avenue for extending that with also angle or position or spatial coordinates?
Yes. Right. Yeah, that's a good point. So this is another answer to your question. So it would be great to augment Wikipedia so that we have, you know, now we have not just rough geolocation, but we have exact geolocation. We also have a 3D model that we could link in from Wikipedia. We have orientation information and so forth. Yeah, I mean, I'd like to be able to augment every image on the web with metadata that says position, orientation, and yes.
Last question.
Yes.
So Apple has a new map, and it seems that it has some 3D models of the buildings for a couple of big cities. And Google has a new 45-degree aerial maps for some cities like in Pittsburgh. And would it be possible to review the cities using the aerial image?
To rebuild the cities?
Yeah, like because every building you have 4 different views.
To build 3D models.
Yeah.
Yeah, I mean, that's basically what these companies are doing, right? So they're flying planes over the cities. Both Google and Apple are doing this. And each plane has, you know, cameras pointing in 5 different headings. And then you essentially, you know, you structure for motion to figure out the camera positions. And then you do stereo to try to reconstruct 3D geometry. You know, mostly height fields. Most of this started out with height fields, but now they're getting increasingly sophisticated. So yeah, both these companies and others are literally, you know, running computer vision at, you know, world scale, you know, to reconstruct 3D geometry from the air. Now these models, you know, only look good from the air. So you know, once you go down to the ground level, they look horrible. You know, the textures, you know, the models are not detailed enough. So this is another big challenge. How can we get good models from ground as well?
All right. Thanks.